Hey everyone, welcome back to another lesson in MCV4U. Today we'll be looking at an introduction to vectors. So first what we'll do is we'll look at a few different terms that are important when we're looking at vectors, its definitions, and the examples which are shown on the right. When we think of the concept of vectors, a vector is a quantity that includes both direction and magnitude. So includes both direction and magnitude. The start of the vector is referred to as its tail, while the end of the vector is referred to as its head or tip. And this will come important when we're looking at how to calculate vectors and understanding where the tail and the tip or the head is. When we think about magnitude, the magnitude is the part of the vector that represents its size or value. And here, magnitudes are always positive, so no matter what, we're taking the absolute value of this size or value. Again, magnitudes here are always positive. And then direction would be then the part of the vector that represents the way that it moves. So does it move forward? Does it move backwards? Does it move north? Does it move south? Those are all directions, and directions is identified by, again, looking at the vector sign, or its bearing. So if we look at this example that is provided for us on the right, we see that it goes from A to B. A would be the tail, and then the end of the vector, which is at B, would be its head or its tip. Here we see that the magnitude from A to B, so that's the size or the value, again, is 20 kilometers per hour, and we see that that is positive. The direction here, we can see the direction that it's moving. It's 40 degrees and it's north of east. So north of east. The next thing we'll look at here is a scalar. So scalar is a quantity that is represented with only magnitude and there's no direction. And so here, if we looked at the first example, we saw that the vector AB was 20 kilometers per hour and it was 40 degrees north of east. Here, in this example, we have velocity 20 kilometers per hour, 50 degrees north of east. That would be the entire vector. But if we're just looking at the scalar, we're only looking at the magnitude. So in this situation, the magnitude would only be 20 kilometers per hour, no direction indicated. A geometric vector is a vector that is not related to any coordinate system. So there's no points that are related here. Again, these vector directions are usually defined using bearings, and we'll look more at bearings below. Again, bearings really mean, again, using things like north, east, south, west to help us identify, again, the direction that it's moving. An algebraic vector is a vector that is drawn in relation to a coordinate system. So it would be on a coordinate plane, and we would put the actual coordinates based on what is provided. So in this situation, the vector, if it starts at the origin, it's at 0, 0, and then it moves to negative 3 to 4. That's where the tip is. So then here, see that the coordinate is at negative 3 and 4. And if we used Pythagorean theorem, we see that it is 5 units in length here. So next thing we'll look at is equal vectors. So equal vectors are two vectors with the same magnitude and direction. So same magnitude and direction. So here we see that vector A is equal to vector B. And so here we see that vector A plus vector B is equal to 2a, which is equal to 2b. So again, they're equal, so which means that they have the same magnitude, same direction. So here we see that for vector a, then it starts from the left and then moves to the right. Same with vector b. So look at opposite vectors are two vectors with the same magnitude. So again, the length or size is the same, both opposite directions. So here we see that, again, same magnitude, but opposite directions. So here we see that vector A moves from left to right, but vector B moves from right to left. So here we see that vector A is equal to negative vector B. And so therefore, we know that vector A plus vector B, when they're opposite vectors, will be equal to 0. So here we're looking at the next thing we look at is collinear vectors. So these are vectors that are parallel and can be translated to lie on the same line. And so here, the idea of parallel and collinear are used interchangeably. And so here we see that vector A is collinear or parallel to vector B. Then finally, zero vectors are vectors whose overall net change in displacement is 0. So signified with the notation 0 with the arrow on top. So again, overall net change in displacement is 0. So here in this situation, we have angle A, angle B, and then angle C moving in these different directions. And so angle A plus angle B plus angle C equals to 0. Okay, so we mentioned bearings a little bit at the top. And so bearings are often used to describe the direction of a vector. Here, if we look at this example, it says again, the bearing n 23 degrees W is read as 23 degrees west of north. So again, a bearing always has three components that we have to consider. Again, number one is the direction it is measured from. So here we see that it is north in this particular case. The angle, which is 23, and the direction which it is measured. So again, you see here we have our north, our angle of 23 degrees, and then the direction towards which it is measured. So if we draw a diagram of what this will look like on the right, so here if we have north, east, south, and west, here again we see that it is 23 degrees west of north. So again, 23 degrees west. So leans more to the west from the north. So here, this would be 23 degrees. So here, if we look at this, so S 20 degrees, E again means 20 degrees east of south. And so here, if we're going to draw this bearing, here, again, label north, east, south, and west. And so here, this is 20 degrees east of south. So it goes closer to the east from the south. So again, 20 degrees. Okay, so here, just a little bit note, it says the most formal way to express a bearing is to measure starting from either north or south. Okay, so here, these examples, it says draw the following vectors to scale, include your scale. Okay, so here the vector is given to us at 30 kilometers per hour at a bearing of 40 degrees east of north. So here if we draw, well, again, north, east, south, and west. So here we see that it's 40 degrees east of north. So it's closer to the east. So here this is 40 degrees. And here, again, our vector quantity is 30 kilometers per hour. Here, this next one here, we see that we have our vector quantity of 40 kilometers per hour at a bearing of 7 degrees west of south. So here we'll label north, east, south, and west again. And so here this is 70 degrees west of south. It's closer to the west from the south. Here it is 70 degrees, and our vector quantity is 40 kilometers per hour. Okay, so when we think about scalar, which is the magnitude only, versus vector, which is magnitude and direction, when we're looking at the comparison between distance versus displacement, so distance is our scalar quantity, and displacement is our vector quantity. When we think about speed versus velocity, speed is our scalar quantity, and velocity is our vector quantity. And then temperature versus temperature change. So temperature by itself, scalar, and temperature change with direction. So temperature change with direction, like positive or negative, would be a vector quantity. When we look at mass versus weight, mass would be our scalar quantity, and weight is our vector quantity. Then if we look at multiple things for scalar, and it'd be something like time, energy, work, and for vector quantity, be something like force, acceleration, and momentum. Okay, so continuing on, when we're looking at vector expressions here. So again, imagine you want to walk across a path in the shape of a parallelogram shown from point A to point C. So from point A to point C. Regardless of which path you follow, your overall net displacement is the same. So here, again, displacement, and here is a vector. And again, note distance is a scalar quantity. So that means that one vector can often be expressed in a number of different ways, again, using different vector expressions. Here it says determine a vector expression that represents each vector. Okay, so here, one thing to note, again, is that we want to add vectors want to add vectors tip to tail, never tail to tail. Okay, so here, when we are trying to determine a vector expression that represents this particular vector, vector AD, we see that we go from AD, so vector AD. So here, if we go from A to B, from tail to tip, we go from B to C, which is tail to tip, and then we go C to D. So go from A to B, tail to tip, go from B to C, which is tail to tip, and then we go from C to D. And so here, if we write that out, we see that we go from A to B. So that's our first vector, A to B, plus B to C. That's our second vector, plus C to D. And here, what you'll notice is that what we're looking to get to is vector ED. And so here, we know that A is our tail and D is our tip. So if you write these vectors correctly, you'll notice here that it starts with the tail and ends with the tip. And what we'll notice here is that in each vector, it goes from tail to tip. And so here in vector AB, you see that our B value is our tip. But then in vector BC, our B value is tail. And then our C value becomes the tip. And then in vector CD, again, our C value then becomes the tail. So here we see that when we look at the sum of the vectors, vector AB plus vector BC plus vector CD will give us vector AD. Okay, so the next one, if we look at E here, we're looking at vector CD. There's a couple things we can notice here and that we can write down. So here, vector BC, we can also write as negative vector CB. Or we can write it as vector CB is equal to negative B vector BC. Here, so we also can write vector AB is equal to negative vector negative BA. So here we're looking again from C, which is our tail, to D being our tip. So looking from C to D. Looking from C to D. So if we go from C to D, so here we can go from C to D. Again, we go from start at C, we go C to B, then vector B to A, and then vector A to D. Here, if we could write the vector CD is equal to the sum of the vectors, vector CB plus vector EA plus vector AD. And here again, we see that it starts with the tail and ends with the tip.